All right, so this is one's going to seem a little bit out of place if you follow along with the Larson book, thinking that that's just the way that calculus is done. Because for some reason, Larson decided, hey, you know what? Let's skip all the way to chapter 3, section 5 to do limits at infinity. So, I mean, what follows after this section makes a lot of sense to follow it there, but I think it makes a lot more sense for all the limit things to be around where the limits go. So, limits at infinity. I guess I suppose, just like infinite limits, these are really weird. So the difference between the two, infinite limits, these mean that the answer will be negative infinity or infinity. Okay, so that's how that goes. The limit as x approaches c of f of x equals infinity, for example, would be, that's an infinite limit. Now, a limit at infinity flips it around at infinity. So the idea for a limit at infinity is, instead of y approaching infinity or negative infinity, x is going to be approaching infinity or negative infinity. Nobody. No. Daddy's working. Daddy's working. Come on. Go play. And this will come out to be some number, typically. So the idea then is that both of these are talking about infinity. The difference is that this is talking about a vertical asymptote, while this one is mainly talking about horizontal, but could also discuss and slant asymptotes. Mainly when it actually comes out to be a number is we're talking about the horizontal asymptote. That's where that comes in. But slant asymptotes too also will do this. And there's some funny different horizontal asymptotes. The real thing about asymptotes that people just get all mixed up, because when they first learn about asymptotes, they learn about vertical asymptotes, and somebody tells you can't touch the asymptote. The graph cannot touch a vertical asymptote. True, because the function is undefined there. That's why what makes it so significant. However, a horizontal asymptote, or even a slant asymptote for that matter, takes on a slightly different approach overall, and for the most part, the thing is about asymptotes, okay? So think of it like the pirate code. So asymptotes are guidelines, okay? These are guidelines. These are what the graph will follows. As one value is going to infinity, what's going on? Sometimes x is going to infinity, sometimes y is going to infinity. But that's so in horizontal and slant asymptotes, x is going to infinity or negative infinity. For vertical asymptotes and slant asymptotes, y is going to infinity or negative infinity. So this one's doing both. But that's the idea of what's going on here. So basically, if we talk about graphs, and graphs are the nice easy way to start about it. And so let's say we had, say, a population of something, I don't know, reindeers or something. So what's going to happen is that the population, and if you've studied biology, then you understand the limiting value of a population size. Now, sometimes that needs to be regulated, so that way, because of other things, that's why if you go to certain places, if you had a problem with deer hunting, well, actually, it's a good idea to do that, because otherwise, if there's too many deer, then they'll eat too much food, and you'll have starving deer, which then leads to disease. So that's not a good thing. So even if you have a hard time with killing Bambi, understand that it's just part of nature. So in order to maintain itself, but either way, and you also understand too, and I'm sure Mr. Wolning explained it to you, that when you have these things in real life, it bobs up and down. Sometimes, like say the limiting population of reindeers was 100. Well, then sometimes it's going to be, it's actually going to be like 102 or 98 or something like that. But it's going to kind of bounce up and down through there, and that's okay, because it's still an asymptote. Because what it's saying is that this is a guideline, and so what we would say is that the limit as x approaches infinity, or really in this case, it'd be better to call it t if we're talking about population. As t approaches infinity, our population of reindeer, p of t, is going to end up being 100. That's what it happens. And so in the long run, the population basically be right about 100 reindeers. So that's how that goes. Now, which is easy to look if you see whenever you see a graph, you look at the horizontal asymptote. It's going to be drawn out there. You see it with different things: population, cooling, because things like second law of thermodynamics is true, and so things just kind of balance out. That's another one that you'd see where, let's say, something starts off cooling, and what's going to do is it's going to end up cooling off, and so then you end up with this cooling temperature, and let's say it's like 70 degrees, and so you'd see that, like, oh hey, the limit as t approaches infinity of the temperature as a function of t is going to be 70 degrees, and so eventually it's going to cool off to be about 70 degrees is the idea. That's where you see it graphically, and that's what makes the easiest amount of sense. Now, if we're, of course, numerically, you can always plug in bigger and bigger values and make charts that, if you want to make charts, you put in things like, x, and we'd have f of x. And then we say, let's put in 10,000, and let's say it comes out to be 5.001, and we put in 100,000, and it's like 5.0001, and then you're like, what about a Google Yeah, so that's a Google. So then you end up with 5 point, 0, 0, 0, 0, 0, 0, a whole bunch of zeros, 1. And you can see what's going on is that eventually it's going to basically, we would say, hey, that the limit as x approaches infinity of f of x is 5. And so even though we can't ever get to infinity because none of us is Buzz Lightyear, we can talk about what's going on and what we're approaching and what eventually the trend is going to do. Yeah, furthermore, nobody could actually get to a Google. Well, definitely not a Googleplex. So if you know what a Googleplex is, that's like actually one of those things. It's a number that's so impossibly big, but it's still less than the idea of infinity. Hey, Joshua, let go. You're fine, Emma. Calm down. All right, so now let's talk about analytically. There's a couple different ways of going about this. Personally, I prefer to talk about a certain concept. Let's say we say 5 over x squared plus 7. Okay, so the idea here is if we're talking about what's going to happen as x approaches infinity, the top of this is going to be 5, while the bottom is going to be infinitely big. And so the idea is that, well, if I take 5 and I divide it by something infinitely big, then it's going to end up being 0. So here's a little thought experiment that I like to do. So suppose we have a pizza. Okay, got pizza. Okay, let's say you're feeling really generous, and so you go, you gather together, your $5.40 or $5.45, depending on where you live or shop, and you go over to Little Caesars and you get yourself a hot and ready pepperoni pizza, and you decide that you want to be super generous, and you are going to send this pizza to share with everybody in China. Okay, there's my picture of China. That's where Mongolia is. So you're going to send it to everybody who lives in China, and they're going to get to share that one pizza. Well, if we take all the different Chinese that are there, okay, and we give them that one pizza, then what's going to happen is basically everybody's going to get, even though they would officially get something, they would essentially get nothing. And that's the idea about these limits as we approach infinity. You take something finite and you divide it by something insanely big, and you realize that basically boils down to nothing. So that's the concept there. So now with this, then, if we say, okay, well, that's just 5, but what if instead we did something like, hey, what's the limit as x approaches infinity of 5x divided by x squared plus 7. Okay, so now let's take a look at this one. So it's a little bit different because that top part is also going to infinity. I'm like, okay, yeah, this is true. But here's the deal. Okay, let's take a look at this. So imagine somebody who's got a lot of money, Bill Gates, Oprah, whatever, and you felt like you wanted to be really, supportive, and you wanted to donate money. So you donated $7 to the Bill and Melinda Gates Millennium Foundation. Well, good for you. I hope you feel better about that, but they don't need your money. In fact, actually, that $7 wouldn't affect them at all. They might not even cash that check. So what that means is that in the long run, even though 7 is more than whatever this was, relative to infinity, it's insignificantly more. It doesn't matter. And so what ends up happening is 5x over x squared. And so there you go. Mathematical proof that you do not matter to Bill or Melinda Gates. So no matter how much they try to convince you otherwise. Okay, now the limit as x approaches infinity now of this. Well, you're looking at this and you've passed algebra, otherwise you wouldn't be looking at this. And we say, hey, the limit as x approaches infinity of, well, then we could reduce that. Now it's 5 over x. And now we're back into that same boat where we're taking a finite number of things, 5, and we're dividing that by an infinite amount of things. And so we can see that this comes out to be 0. And so although this and this are not equivalent, these two things are not equal, when we're talking about the functions are not equal functions, but equal limits is the idea. And so these two things are definitely going to come out to be equal. You could also talk about the squeeze theorem too and say that this is less than that, but this is greater than 0 when we're talking about infinity. And since this is going to go to 0, and the limit as x approaches 0 is going to go to infinity approaches 0 is going to go to 0, this is going to be squished between this and the 0 line, and so it's going to also go to 0 as well. That's the squeeze theorem in a nutshell. So there's that. Now, what about if we had, say, the limit as x approaches infinity of 5x squared minus 2 over x squared plus 7? Okay, so this is a little bit different too. Again, minus 2. Now, of course, The Simpsons told us that Bill Gates didn't get rich by writing a bunch of checks, but if he lost $2, if $2 fell out of his pocket, he probably wouldn't notice. So those $2 don't matter if you were to lose it. And we already talked about how the $7 doesn't matter. So essentially this comes out to be the limit as x approaches infinity of 5x squared over x squared. And so same concept as when we approach infinity, these things do not matter. And so then this comes out to be, we could do, hey, that's just the limit as x approaches infinity of 5. We reduce that, and that's going to be 5. Okay, not too bad. Now what if it's a little bit different? The limit as x approaches infinity of 5x squared plus, or minus 2x. Well, that's different because now we got that x there. And we got x squared plus 7. All right, so here's the deal. That 2x, compared to the 5x squared, if we're talking about numbers that are insanely big, this also is completely insignificant compared to that. And for proof, let's take a big number, like, a big number, not even a really, really big number. We'll take, we take a billion. A billion has 1 followed by 9 zeros. That's a billion, okay? So if we had 5 times a billion squared will end up having 18 zeros. So that means 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, like that. We're going to subtract 2 times a billion, so that's going to be minus 2 billion, okay? So we have that. And then what would happen is we'd end up with 4, let's see, it says billion, trillion, quadrillion, quintillion. So 4 quintillion, 999 quadrillion, 999 trillion, 998 billion. You know, so whatever. Okay, so this, if we were to put this into scientific notation, we would have 4.999999998 times 10 to the 18th power. Well, you've taken enough science classes to understand that you would not write all that out. Okay, significant figures and whatnot. You wouldn't write all that out. In fact, actually, if you try to type that into most calculators, you run out of space. It wouldn't actually do it. So you can understand that that's still basically just 5, quintillion. So this 2x really didn't do anything to this. Percentage-wise, that would be nothing compared to that. So because of this right here, anything, all that matters is the thing with the highest power. So all you do is you take the thing with the highest power from both the top and the bottom, and then we reduce that fraction, and we end up being able to figure out the limit. That's the idea. Take the things with the most power, reduce the fraction, find the limit. Now, one last weird thing that could pop up. So let's say we got the limit as x approaches infinity of 5x cubed minus 2x squared over x squared plus 7. So basic idea, all we do, take the thing with the most power. So 5x cubed. This is insignificant compared to that. Same reason. X squared. We reduce this, and so now we have the limit as x approaches infinity of 5x. Is what that reduces to. And as we put in, as x gets bigger and bigger, this will increase without bound, meaning that this will go on to infinity, or we could also say it does not exist. And that's the concept of limits at infinity. So thank you. Hope that helps. For both directions. So limit as x approaches 0, and we'll go with x over the square root of x squared. Okay. Now, square root of x squared. Well, you know what? Let's make it a little bit plus 2x. Okay. So again, in the long run, that 2x, is it going to matter? No, it's not going to matter. So this is going to be the limit as x approaches infinity of x over radical x squared, because that 2x won't matter in the long run. And this, now, here's a question, and this might surprise some people. What is the square root of x squared? The square root of x squared is the absolute value of x, not just x, okay? And there's another reason why you can't just cross things off and use the C word and what those things do right there. This is because, all right, we define the function f of x, this right here. This is, okay, f is for, okay, I'd accept either friends who do things together or for function, but in this case it's for function. That means that there can only be one output, which means that it has to be, f of x has to be greater than or equal to 0. It's got to be positive or 0. In this case, obviously, since we're approaching infinity, it's going to be positive, which means that has to be positive. If we were just to cross these out, if we're approaching infinity, it makes no difference, because then we're going to have, this is going to be, that is going to come out to be the limit as x approaches infinity of x over x, which is just 1. However, if we look at the limit as x approaches negative infinity of x over radical x squared plus 2x, and again, that 2x is insignificant compared to x squared. We're approaching negative infinity. Now we're at x over radical x squared, and this comes out to be the limit as x approaches infinity, negative infinity of x over the absolute value of x. On top, that's going to be -1. Okay, we're going to have, this is going to be a negative value. This is going to be a positive value. These are going to be opposites of each other. And so a negative divided by a positive is going to be a negative. And then this, because we're dividing x by x, the values are going to end up being the same value, but opposite values. So that's negative divided by positive. We end up with -1. And what ends up happening is this weird graph. This sort of thing makes a kind of a weird graph where you actually have two horizontal asymptotes in it, which is kind of funny. On the one side over here, it does that and approaches that one, but on this side, it comes towards this side, and so we actually end up getting this sort of thing going on here like this, and it's kind of funny like that. And so this is the really interesting one when you have the square roots. And so this right here is the trick, that the radical x squared equals the absolute value of x, not just x. So keep that in mind as you go forward, and let me know if you have any questions.